Shall we start?
Hello. Thank you, Grishma, for the introduction. Uh, I'll be talking to you about uh, not precisely about philosophy of science, but it is basically an introduction to philosophy of science. Uh, what makes it different is that when you are taking a class on philosophy of science, it is the content will be different. But this particular session, I am interested to tell you what philosophy of science is doing and how that particular branch of inquiry has got a bearing on the work which we are doing. I think most of you are researchers, and my interest would be to see how philosophy of science has got a bearing on your work which you are doing. I'll be putting up the presentation right now. I hope you can now see the slide. Grishma, could you confirm? Can you see the first slide?
Yes, sir.
Okay. So basically, this is introduction to philosophy of science. Now, one of the first questions which comes to our mind is to define science. What is science? Science is normally defined as a empirical inquiry to understand the world around us, and it's basically a knowledge system. Science is a process by which we create knowledge, document it, and understand uh, as best as possible the world around us. Now, when I say that science is a knowledge system, we should also understand that there are other knowledge systems also. Can you think of any other knowledge system other than science? Very interestingly, these days, there was an interesting case where homeopathic medicines were distributed by many of the government departments as a way to defend the COVID pandemic. Now, there was a question which one of my colleagues asked me, how do you agree with this process of distribution of homeopathic medicines? The question is very valid in the sense that homeopathy is a knowledge system which is not approved by modern science. Many of the fundamental principles of homeopathic medicines is not agreeable to modern science. For example, homeo medicine, even when tested in the most sophisticated equipments, could not come up with any single molecule of any active medicine. You just have the medium there. So modern science doesn't understand how something which doesn't even have a single molecule of a particular active principle can cure a disease. And second and most important is that the homeopathic practitioners believe that whenever you dilute something to a very high level of dilution, the potency increases, which is absolutely against the knowledge of modern science. Modern science thinks that whenever a substance is in a very high dose, the impact will be very high. And when the dose gets reduced, the impact goes down. It is the absolute opposite in the case of homeopathic system. Homeopathy is another knowledge system. Ayurveda is another knowledge system. And there are many traditional knowledge systems across the world. So what I'm trying to say is that while modern science is a knowledge system, there are other knowledge systems also existing. The second distinction which we need to make is between science and technology. Normally, we say that say these two words very close together, come close together, and it is almost treated as a single thing. Now, the difference is that the mandate of science is quite different from the mandate of technology. Science basically tries to explain the world around, while technology tries to make gadgets which will make our life much more easier. This is a very cardinal point which I will explain with the help of a few scientists. You might know about Albert Einstein and his famous equation E is equal to mc square. He was basically a scientist, and he was trying to explain through the equation a process which is happening, a phenomena which is happening in nature. Now, it was whether you know E is equal to mc square or you doesn't know about that particular equation is not going to have any serious impact on your life. So he was trying to explain nature. You might also be knowing about another scientist, another person called Thomas Alva Edison, the man with the largest number of patents hitherto. And he was basically a technologist. He was producing gadgets, starting from the electric bulb, a series of many different things, which makes our life much more easy. So we call Einstein as a scientist, and Edison is a technologist. Coming to India, you have heard of a person called C.V. Raman. C.V. Raman, the Nobel laureate, was a person who is considered to be a scientist. Basically, he was trying to explain what is happening in nature. For example, with a very simple question which he asked, why is the sea blue? Now, people believe that the sky is blue and the sky is getting reflected on water. And C.V. Raman proved it is not that way, and he came up with a totally different theory to explain this. Now, whether you know the reason why sea is blue or not, is not going to have any serious impact on your lives. But he was trying to explain a process which is a process of phenomenon which is happening in nature. Now, that discovery had got a large number of practical implications also, but that was not the reason why he discovered it. Now, we also know a person called APJ Abdul Kalam, mostly called as a scientist, but he was basically a technologist. He was not trying to explain nature around him, but he was trying to bring up gadgets for particular purposes. So you have a team and you have the money, and he would pull them up to produce materials in the shortest possible of time. So C.V. Raman was a scientist, APJ Abdul Kalam was a technologist. Now, this is one of the cardinal differences which we need to understand while we move ahead. Now, coming to sciences, you know that it is not just one science. There's a different branches of science. And I'm trying to explain how the different branches of science are connected with each other. The first and foremost sciences is considered to be physics. Basically, because physics addresses the smallest possible form of matter, the atom, and also it looks at the large heavenly bodies like the stars, the nebulas, the constellations. So physics is basically considered as the primary science. And on top of it, we have chemistry. While physics essentially deals with the primary atoms and things at the atomic level, chemistry looks at the whole world from the perspective of the molecules. So when you graduate from physics to chemistry, what essentially happens is that physics has got its own laws, and all the laws will be held intact. But when you graduate to chemistry, you have more laws coming in, while the laws of physics are also integrated into chemistry. Then, when you come to biology, when life comes in, it creates a totally different a platform where you study life in the case of plants or animals. So you come to a totally different subject domain. And when you reach biology, the laws of physics are held intact. The laws of chemistry is also held intact, but it acquires new rules and hypothesis and uh, uh, rules. Then you have the social sciences, a set of sciences like sociology, psychology, economics, history. All those sciences look at something which a single species does, the species which we call as Homo sapiens. When when you deal with the money, how people handle money and the different forms it acquires. You study it in economics. You look at the social behavior in sociology. You look at uh, the transformation in also human societies in the subject called history. So all those subjects come under social sciences. Then on top of it, we have philosophy. And one of the interesting questions is, what do philosophers study? We know physicists study the uh, the cosmic things, the stars and all, including the atom. Chemistry studies the molecules. Biology study life. Social sciences study social interactions. What does philosophy study? What is the basic subject matter of philosophy? And philosophy is very interesting in the sense that when you do your PhD, if you are doing it in botany or chemistry or physics or zoology, the degree you are going to get is called Doctor of not botany, but it's called Doctor of Philosophy. Why is it that uh, earlier there was also a course called Master of Philosophy called MPhil, which is going to be taken out, it seems. So, why do people studying different type subjects end up in getting a degree in philosophy? Basically, because philosophy is a subject that looks at the larger picture. It looks upon the different subjects and try to see what they are essentially doing. Does it make any sense? That is a that is a viewpoint of philosophy. For example, if there's a philosopher in this particular group, that person will not be interested to try hard to understand what I'm saying, but then while doing so, this person will also be interested to look at what this guy is trying to communicate. Does it make any sense? So it's going to be a outsider view on the different sciences. So that is what philosophy does. We should not uh, miss the role of languages. Language is very important in the sense that language is the vessel which holds the knowledge. You have knowledge in physics, chemistry, biology, social sciences, or philosophy. You handle it in languages. You store it in language. You think in a language, and you communicate in a language. So language is very critical in the sense that that's the only way you can hold the knowledge which you are creating. Now, among languages or among sciences, we have something called mathematics. What is mathematics really? Is it a language or is it a science? People think about mathematics as a language and also as a sciences. When it's used as a language, it is used to communicate information. And the beauty of mathematics is that it has got absolutely emotionally neutral. It's an emotionally neutral language. When you use our normal languages like English, Malayalam, Hindi, Sanskrit, and all, each word in that particular language is heavily loaded with emotions, and the meaning of the language can also change based on the context. Like, for example, the largest spoken word in the world uh, is supposed to be hello, and you can say hello in many different ways. You can say hello very sweetly. You can say hello very harshly. You can say hello with a lot of anger. Now, based on who speaks to whom and what is the context of the moment, the information content of that particular word changes in the case of every language. But in the case of mathematics, it doesn't happen. When you say 2 plus 2 is equal to 4, however sweet you say, however harsh you say, there is no loss of information. So mathematics is supposed to be the language of sciences which needs to communicate precise information. And looking at the different sciences over here, for example, physics, chemistry, and biology, they get classified into two big groups. One group is called the hard sciences, and the other is called the soft sciences. Physics and chemistry are basically called as hard sciences, basically because they are predictive. If you launch a rocket from here, if you know the initial velocity, the angle, you can predict where the rocket is going to be after 5 minutes or 10 minutes. And you can use the rocket to put a satellite in a specific orbit. You can absolutely plan the whole process. But in biology, it's not possible. You cannot predict things as good as in physics. For example, I am a person who study insects. Uh, insects basically butterflies, moths, beetles, and all. So even after studying a large number of years about butterflies and moths, if a butterfly sits in front of me, I'll never be able to predict to which direction the butterfly is going to fly. Is going to fly. So biology is not as predictive as either physics or chemistry. Chemistry also is very predictive. If you put two particular chemicals into a test tube, you can predict what is going to happen. But in biology, it's not possible. So predictive sciences like physics and chemistry are called as hard sciences, while biology is called as a soft science. But then these are not watertight compartments. Hard sciences try to reach to the, soft sciences try to reach to the category of hard sciences. They're getting much more and more rigorous. And this process is by intermixing of the subjects. Like, for example, physics and chemistry meet to form a new discipline called biophysics, and biology and chemistry meet together to form biochemistry. Biology merges with mathematics to form biomathematics. It merges with statistics to form biostatistics, and it makes a huge jump and merges with technology to create a discipline called biotechnology. So there are many interlinkages. So what I'm trying to say is that these are not watertight compartments. There's a lot of new disciplines coming up at the interfaces of different subjects. So this is the major framework in which we'll be discussing further ahead about philosophy of science. Now the question is, what does that make something a science? So what's the common property of activities which is happening within science? And what does philosophy of science does with it? Basically, what philosophy of science try to do is to analyze the methods of inquiry used in the sciences. For example, to give you a very simple example, you might be in the pressure of the COVID pandemic, and every day you get to know that a particular number of people have got tested positive. And this information is communicated to the general public on a daily basis. So one of the philosophers in Kerala responded to this particular process by asking a very simple question: what does it really mean to say that a particular person has been tested positive? What does it really mean? So to know and to get an answer, you need to go into the real testing process. What is tested? Using what method, and what does it really convey? So then when you get to that level of information, you understand that there are different types of tests possible. And if you're going for a PCR test, what it essentially does is when you go for a RT-PCR test, what essentially happens is that based on the swabs which have taken from you, from a particular person, the labs test whether that particular sample contained RNA of the COVID-19 virus. How does they do it? They do it in the process of using an enzyme called reverse transcriptase to make a copy. Shall I continue? Hello?
Yes, sir.
Yes. Okay. So basically what happens is that you take the swab, you take it to the laboratory, and you use a reverse transcriptase enzyme to construct a exact copy of a DNA of the RNA strand which is found in the virus. And if that happens, then you use a PCR machine to amplify it and to see whether the based on the primer which you give, you can see whether the RNA is of the particular virus, and you say that the particular person is positive. Does it mean that that person is infective? Does it mean that the person can transfer the disease to others? No, there's no surety in that happen. It can or it may not be. So, and if you're going for another test called the antigen test, it also only communicates that it looks for the specific antibodies there in the blood system. And if it is found positive, it only means that you had been having the disease sometime uh, earlier, so that your body has responded to it. It also doesn't mean that you can communicate the disease to others. So the philosopher asks the question, so what does this really mean when you say that 1,000 people have been tested positive? It only means that when the time of taking the swab, there was uh, the virus traceable in the body. Many other questions are not answered, but it is just this. It doesn't say anything about the transmission of the disease. Now, this is the way. While a particular community, a society, takes up scientific information and uses it, and when a large amount of panic is made out of it, the philosophers ask the question whether this method of inquiry used in this particular science is really valid. What does it actually communicate? This is one way in which philosophy interferes with science. And secondly, philosophical reflection can uncover assumptions that are implicit in scientific inquiry. When we practice science, we take many things for granted, and we move ahead with that. And there's a large set of primary assumptions which we already have, and we will not be able to test all the assumptions which we have. Like, for example, you start working on a particular plant, and somebody tells you that the name of the plant is this one. You agree with that, you move forward with that. You are not really concerned why this plant is called this particular one and when was it called. You never will be testing the whole history of the naming process which has happened. You take it for granted that there's a name of a particular species is A, and you call it A all the while you are doing your work. So hello, madam, talk. Sorry for that. So what I'm trying to say is that philosophical reflection can uncover assumptions. And one point of time in your research, somebody comes up and asks you this, start to question your fundamental assumptions. You call him a philosopher. And as I told you earlier, many of the assumptions which we take as researchers gets questioned when philosophy of science interferes. We will get into in this particular talk. We'll be taking one single example to demonstrate how this is going to happen. But before that, we'll look at the fundamental principles which has evolved in the discipline of philosophy of science. Now, before moving further, we need to distinguish between two different ways in which inferences are gathered. One is the deductive process and the inductive process. You can Google both the words and get to know what is deductive logic and what is the inductive logic. And what is on screen is an example of the deductive logic which is normally used. It goes like this. The first premise is that all Frenchmen like red wine. The second premise is that Pierre is a Frenchman. So therefore, we assume that Pierre likes red wine. And this is the way inference is drawn from a basic set of statements. I'll read it once again. The first statement is that all Frenchmen like red wine. Pierre is a Frenchman. Therefore, Pierre likes a red wine. So this is a simple case of deductive logic. Based on these two first statements, you deduce your conclusion that Pierre likes red wine. And this is what we call as the deductive logic. Opposite to that is the inductive logic, where I have given a different example. It goes like this. The first 5 eggs in the box were good. You have a box with a large number of eggs, and you took 5 from the box and tested whether they are good, and they are found good. Now, you also observe that all the eggs have the same best before date. So the expiry date are all same for all the eggs, and the date is stamped on each of the egg. So based on these two assumptions, you assume that therefore the 6th egg will be true, good too. One second. So on screen are the two different logics, the deductive and the inductive inferences. Now, if you look very closely, you can be very sure about the first thing. In the first case, if both the premises are right and correct, you can definitely go to this particular conclusion that Pierre likes red wine. But look at the second case. The first 5 eggs in the box were good. All the eggs have the same best before date, and therefore you assume that the sixth egg will be good too. Will that be? Now the problem is that there can be chances where the sixth egg can be a rotten egg, because even if these two premises are correct, uh, uh, there's every chance that this can go wrong because you don't have information. You have tested only 5x. And this is why we normally say that science go by deductive logic rather than by inductive logic. And that is the way we draw inferences in science. And coming to the how do you explain a process in science? Uh, Carl Campbell was a person who had thought about this problem in a very big way, and he asked this particular question: what exactly is explanation in science? He's told that it is basically characterizing precisely that the relationship must hold between a set of premises and a conclusion. As we saw in the last slide, there's a set of premises and a conclusion, and this would be a precisely uh, a relationship should be established between the premises and the conclusion. We'll see how it's work. And Hebel says that uh, the first thing, the premises should entail the conclusion. The premises should go in tune with the conclusion. For example, I can also make a statement that about a particular situation, uh, that there was a call uh, by the cock in the morning, and because of that, the sun has risen. Now, when I when I link between a premise which states that in my home, my cock had uh, made a call in the morning, is linked to the rising of the sun, which essentially means that the premise is not entailing to a particular conclusion which I am trying to draw. So the first criteria is that the premises should lead to the conclusion, and the second is that the premise should all be true. All the premises should be true. If any of the premises is false, then the conclusion will also go false. And the premise should consist of at least one general law. There should be one general law, at least one. There could be more in the premises when you draw a conclusion. Now, when you do your research, when you draw up a particular conclusion, this is a test which you need to do to see whether your conclusion agrees with the premises. So what you need to do is to write down the premises and the conclusion, and to see whether uh, these three principles are satisfied. One, the premises should entail the conclusion. Second, the premises should be all be true. And the premises, thirdly, the premises should consist of at least one general law. So this is a simple way in which you can say that an explanation given in science is valid, or this is a way we arrive at explanations in science proper. Now, this guy called Karl Popper is a Austrian-born but British philosopher who wrote a very classic book on uh, scientific revolutions. So Karl Popper was not agreeable to this particular deductive logic thing. What he told was that the fundamental feature of a scientific theory is that it should be falsifiable, which means that you say a statement in science uh, can be, there should be a possibility that it can be uh, checked whether it is uh, false or not. I'll give you one example. If I tell you right now that it is night now, I make a statement, it is night now. You can test it. You can observe. You can go out, you can observe that the sun is out and you can see the light coming from the sun. And you can say that, you can prove that my statement is uh, false. So every statement, statement in science or a theory in science should be falsifiable. Now look at another statement. I say that uh, God exists. If I make that statement, how do you test it? How are you able to falsify it? It's impossible. So you cannot just go out and see whether God is there or not. So this is a statement which is not falsifiable. You cannot prove that it is false. So those statements doesn't fall into the ambit of science proper. This is what Karl Popper was trying to say. Every statement in science which you make could be tested, and it should be falsifiable. Now, he took his basic definition for scientific theories into testing of many of the scientific theories which were existing. And the most interesting and most celebrated are these three theories. One is the Sigmund Freud's psychoanalytic theory. The second is the Karl Marx's theory of history. And third, Einstein's theory of general relativity. Now, the problem, he told that he analyzed all the three theories, and he told that the first two doesn't fall on science. The Freud's psychoanalytic theory or the Marxist theory of history doesn't fall as science, it cannot be classified or supposed to be science, basically because of the fact that both these theories are not falsifiable. That was Karl Popper's major objection. How is it so? In the Freud's case, when he used psychoanalytic theory, you don't disprove the theory, whatever the results of the observations are. Like, for example, if somebody throws a child from a sixth floor of a building, his behavior is also explainable by psychoanalytic theory. And if a man saves a child from the running waters, his behavior can also be explained based on psychoanalytic theory. Or in other words, there is no way in which you can disprove the Freud's psychoanalytic theory. And anything which cannot be disproved doesn't fall as science. This doesn't mean that it should be false, but then there should be provision for falsifying it. You should have a method by which you can disprove a theory. Only then it qualifies as science. And what is the problem with Marxist theory? The Marxist theory says that history moves forward from a uh, uh, primitive socialism to feudalism. It moves from feudalism to capitalism, and from capitalism to socialism, and from socialism to communism. Now, this is a transformative process which Marx predicted. But then when looking around, we see that many places feudalism has moved forward to capitalism, and capitalism is still waiting over there. It is not just getting transformed into socialism. Why is this? When asked why this is not happening, the Marxist theory comes up with new propositions about explaining how this is being delayed or waited. So new additions are coming, but it doesn't say that the theory is wrong. So you cannot disprove Marxist theory. And this is the reason why Karl Popper says that these two theories, the psychoanalytic theory and the Marxist theory, doesn't qualify as science. But in the case of Einstein's theory of general relativity, the things are different. It can be tested. If the predictions which have been done by Einstein based on general relativity can be disproved because there's a specific set of theories which has or predictions which has come from Einstein's theory. And if any of the observation goes against it, you can say that the theory doesn't work and the theory can be falsified. So Einstein's theory has the option to get falsified based on the data collected through experiments or observations. But in the case of Freud and Marx, there's no way in which can disprove the theory. So this was the Karl Popper's objection, and he was of the view that the fundamental feature of any scientific theory is that it should be falsifiable. Now, there was an interesting case which happened later when each of the planets of the star Sun was being identified, and when Uranus was observed, people observed that it was going in an elliptical path. But based on the theory on attraction of different bodies in the universe, and based on the other planets and the position of Sun and the force exerted by the other bodies on Uranus, people observed that the path of Uranus is not explainable. It was moving in a totally different path. Now, this was a classic case in which you can look at it and say that see the the planet Uranus is not moving in the same way which has been predicted by physics. So what can do as per Popper's idea, you need to say that the theory is wrong. The theory which is put forward by Newton was wrong. That is basically the decision which has to be taken. But what really happened was that in 1846, Adams and Leverrier predicted that this behavior of Uranus is basically should be because of the presence of another object which has not yet been discovered. And what happened was that this led to the discovery of another planet called the Neptune. So here, looking closely, you need to understand that, see, this is a classic case in which there was an existing theory, and when you, based on the theory, when you try to look at Uranus, you are not able to explain the behavior of Uranus. So instead of saying that the theory is false, what Adams and Leverrier did was to use the same theory and to predict there is something else which is yet to be discovered, and they discovered Neptune. And this was the classical case against Karl Popper. So when you say that Freud's theory or the Marxist theory is false, is not falsifiable, philosopher says that that is not the way things move forward. Whenever a data comes up to say that a particular theory is not really trying to explain, you expand the theory to accommodate the new information which is also coming in. Or, as in this particular case, you look for a new object which is yet to be discovered. So, discoveries in science happens within a theory, and how theories evolve is something which we are going to see next. So basically, to summarize what has been told until now, basically the way science move forward is that it will have general laws, and then it will have particular facts, and then you will have to have a phenomenon to be explained based on the general laws and particular facts. I'll tell you one small example. For example, one student once gifted me a small plant in a small cup. I had put it in my table over here. So after some time, what happened was that the plant wilted and it completely dried up and it got dead. Now the question is, what was the reason why the plant died? So if you and if you need to have an explanation, what we normally say is that there was no way in which sunlight was available in the space, and without sunlight, it will not be able to do the process of photosynthesis. And if photosynthesis doesn't happen, it will not be able to make carbohydrates, the food needed for survival. And if that process is stopped for a reasonable period of time, it gets improvised or died. Now, this is a way in which we explain. We have a general law. There are true laws. There are two true laws which I used in this particular explanation. One is that sunlight is needed for photosynthesis, and the second true law which I used was the statement that photosynthesis is needed to produce carbohydrates. So based on these two general laws and the particular fact that the plant has died, I come up with an explanation. So this is the way science normally operates. You have general laws to explain the behavior. You have the laws which in front of you, and then based on these two things, you explain the process or the phenomenon. Now we move over to very interesting discussion which had been in operation for science for a long period of time. It's basically between realist and anti-realism. Now, here the question is, what are really the scientists is studying? As we defined science earlier, science is basically an enterprise to understand the nature around us at different levels, at particle level, at level of molecule, at the level of living organisms. So that's the way we defined science earlier. Now, there are two different schools of thought: the realist school and the anti-realist school. And the realist school says that the aim of science is to provide a true description of the world. So that is the realist position. And when you come to anti-realist position, they say that the aim of science is to find theories that are empirically adequate, that is, which correctly predicts the results of experiment and observation. The essential difference is that when the realists claim that we are really trying to understand nature, anti-realists say that you cannot do that. You cannot really understand nature. But and that is not the purpose of science. The purpose of science is to find theories that are just empirically adequate to explain the things. So you are not really understanding the way nature works in its entirety, but you are having theories based on which you can explain what you essentially see. So when realists say that science tries to understand the underlying nature of reality, uh, and the realists say that no, scientific theories are instruments for helping us predict observable phenomena. If you have got a particular phenomena, you have a theory which will explain it. But that doesn't essentially mean that that is reality. Now, this is a major shift between realist and anti-realist schools of thought. We already have substantial knowledge of unobservable reality. That is the position of the realist. So you know that atoms are there, you know molecules are there, you know the interactions. So that is what the realist school what the realist school says, that no, you don't have you have never seen a molecule, you have never seen an atom, you have never seen a neutron, you have never seen a quark. So but you have theories on that, and so it doesn't mean that it is just your theory which really explains the reality. But this is fine. You have the theory which can explain some of the things which are happening. It is just that is the anti-realist tool school. And the major difference comes in practice is the last point which I have written over there. While the realists claim that models help us to gain traction of approximate truth rather than exact truth. Before that, go to the other argument by the anti-realist. Much scientific theorizing involves the construction of models which make idealizing assumptions. So anti-realists claim that in science, we need to create models. And these models doesn't really capture reality. For example, the models created for climate change. The climate change model has got a large number of variables. So you cannot take all the different variables to this exact values. For example, uh, how do you calculate the average temperature of the planet? Uh, Under the discipline of climate change, we say that the average temperature of the planet is increasing, and it has increased by 1 degree. Now, how do we know that? How do you do these measurements? Have you measured every point on the planet to calculate this average temperature? To get an average, you need to average it across a large number of values. So how many values have you calculated, measured? Have you measured the temperature in all the space on the planet? No, you have only a very little measurements. So based on that, you make an assumption. So by itself, it doesn't capture the entire reality. So anti-realist says that, so see, your models are not real models, but good, they are assumptions. They are good assumptions, not a big thing. You are not essentially capturing the reality. What you're trying to do is to make a model which will work, which can predict some of the things which are happening. So what essentially scientists are doing is not to understand the real reality, but to have empirical theories which will say how the things are behaving. So this is a major difference. So realists also realists say that the models, even the climate model, it helps to gain traction of the approximate truth rather than the exact truth. They also agree with that. It's not the exact truth. So basically, science is not a pursuit of exact truth. You are not going to a point at which you are going to identify the real truth out of something. But what you are pursuing is an approximate truth. And once you have it, you then work again for a better approximate truth. So this is the way science is progressing. So don't think that science is an enterprise which is going towards identifying the ultimate truth in nature. Now, before moving further, please take note of these two words, observing and detecting. Observing, you can observe a tree, uh, you can observe an animal, you can observe a bird, you can observe a snake, uh, but then uh, you cannot do that with many other particles which we do science with, like for example the quarks, the atoms, so the molecules. So what essentially happens that there, what you normally do is to detect it rather than observing it. And this distinction has to be borne in mind when you do your field work, when you do your laboratory work. See if what is actually what you are doing. Are you really observing, or are you really detecting it? So this makes different realities for you. If you're observing, there is one part of the story. If you're detecting, that is another part of the story. So be sure what you are doing, whether you are observing or you are detecting. Now we come to the logical emphasis philosophy of science, wherein there's a distinction between two things, and we are going to come to the uh, discovery by a particular scientist. Before that, we need to know this. In any new discovery, there are two things. One is the context of discovery, which is actually the historical process by which a scientist arrives at a given theory. So that's the context of that particular discovery. And then there is another part to the discovery, which is the context of justification. And that is a means by which a scientist tries to justify a theory once they have already arrived at it. So you have a theory, and there's a logical process, historical process through which you reach that particular theory. Now that is not enough. You should be able to justify that theory based on uh, uh, based on data. So these are two different things. The best example is the Kekule's structure of benzene. You might have heard this story. So to make the structure of benzene, uh, Kekule told that I got it in a dream. I dreamed that a snake was found eating itself. So that formed a chain. So I found that I was trying to put this structure together. But immediately in the dream, just after the dream, I realized that this could be a way in which a circular structure is possible. I have never ever thought about it, but the dream gave me that idea. So I used that. Now that is this is a case where uh, it is that discovery was not a logical conclusion of things based on which he arrived at it. It was a flash moment, uh, something called an intuition, something a dream, which gave an idea. Now science cannot stop with that. What makes science different is that you he should be the who should be able to justify that theory holds strong. There's a process in which he had to prove that the circular structure is in place. So this is a way science operates. The original idea can come through a series of iterative process or observations or data, or it can be a flash moment where you strike an idea. But science always go with the next thing. There should be a context for justification. You need to justify whatever you have received, either through the historical process or through an intuition or a dream. So you need to prove that your theory holds good based on data. And the name of the person is Thomas Kuhn, a person who you should read if you are interested in philosophy of science, wherein he brought the idea of a paradigm. And what's a paradigm? A paradigm is a set of fundamental theoretical assumptions which all members of the scientific community accept. So when we do research in chemistry or physics or any sub-discipline of any of these subjects, there are a set of assumptions which everybody agrees to, and that is part of the paradigm. And it's also a set of examples or particular scientific problems which have been solved by means of those theoretical assumptions, which will appear in the textbooks of the discipline in question. For example, I will give you an example of the Darwin's theory of natural selection. So before the coming up of the theory, either by Darwin or Wallace, people had a belief that every species was created individually. The God created them. So that was the. Now there were a large amount of data coming up, which speaks about the interconnectivity. And when Darwin published his results in the classical book called Origin of Species, there was an immediate paradigm shift, and the new paradigm was formed. And that paradigm got the acceptance of the scientific community. So the Darwinian theory can be treated as a paradigm because it has a set of fundamental theoretical assumptions which all members of the scientific community accept. It is true. And it also have a set of exemplars or particular scientific problems which have been solved by means of those theoretical assumptions, and which will appear in the textbooks of the discipline, which are absolutely agreed and taken forward. You have Darwin's theory in our textbooks, and we have solved a large number of problems in biology using this particular theory. So that's a paradigm. Now, what Thomas Kuhn tries to say is that when we do science, which is normally called as normal science is a science which we do within a particular paradigm. So if you're looking studying evolution, if you're studying behavior, if you're trying taxonomy, if you're trying to classify organisms, you all do that within the Darwinian paradigm. So that is what is called as normal science. So whatever you do, you make sure that it agrees with the dominant paradigm at that particular point of time. So this is what is called as normal science. So there's another type of science which is called as a revolutionary science, which changes the paradigm. And this change happens when in a particular scientific discipline, a large amount of data is being produced, which doesn't go well with the existing paradigm. So initially what happens that if there's a very few data which goes against the paradigm, it will be absolutely ignored. It will be just sidelined. But as time moves forward, as new data comes in, if the data goes fundamentally against the against the paradigm, there will be a point at which you will have to change the paradigm. And that change process is called as doing that particular shift is called as a revolutionary science. And Kuhn's theory of scientific revolution says that science goes through a process of normal science for a long period of time, and then there will be enough accumulation of data which goes against the existing paradigm, which makes a shift possible into the next paradigm. And there are two things which are the two words which you need to be familiarized to understand Kuhn's theory. One is incommensurability. Incommensurability is that a particular theory is present. There's a paradigm which is already accepted, and then there's a large amount of data coming up which cannot be explained based on this particular paradigm. So a new theory comes up, and the new theory which is coming up doesn't go along with the earlier theory. It's totally different. uh, uh, in physics, the drastic shifts which has happened between the Newtonian worldview and the view worldview put forward by Einstein is totally incommensurable. Like for example, mass. Mass is defined in the Newtonian sense. Mass is something totally different. In the Einstein's theory, mass is something totally different. So these two theories doesn't go together. That is what is called as incommensurability. It cannot go together. And the second word you should be familiar is the theory ladenness of data. What Quinn says is that when you are operating in normal science, whatever data you collect, the process of collecting the data will have the theory ladenness. You'll be doing it within a particular theory. So when you go out and collect your data, you are consciously doing it well within a particular paradigm. So there's a theory ladenness. This theory is already inbuilt in you, and when you go and collect your data, it's not a process. It's a process in which you are operating within a particular paradigm, and the process of collecting data and the collected data itself has got theory embedded in it. So that is theory ladenness. So these two things are very cardinal to the theory of Thomas Quinn, and he says that a paradigm shift happens and scientific revolution happens whenever the incommensurability is at its peak, and when science break away from the theory ladenness and move over, it forgoes the earlier theory and moves over to making a new theory to explain the data which is piled up. Understanding science as this process, and this man made a big difference for Paul Feyerabend. Against Method is the name of one of his classical books. He came up with a totally different perspective for science. He says that there is no single prescriptive scientific method, which is absolutely shocking. And he also argued that any such method would limit the activities of scientists and hence restrict scientific progress. As we have seen in the earlier slides and in my talk, uh, uh, we have seen situations where people try to theorize and science try to wriggle out from there. You define science as a process of explaining nature, and then there was an argument that no, you are not really explaining nature. What you are doing is to just make theories which will really work, but that has nothing to do with what actually nature is. So that type of complications came, and then it was taken forward by saying that there's a process of doing normal science, and then there's a time at which you need to jump over from one theory to the other, and that is called a scientific revolution, as explained by Thomas Quinn. But then Paul Feyerabend said that you cannot just give prescriptions on this is the way science has to be done. For him, science is basically an anarchist enterprise, a process in which anything goes, any method is possible. Basically, he says that science would benefit most from a dose of theoretical anarchism. And he had studied specific scientific revolutions for putting forward his argument. For example, he refuted the claims of consistency. Consistency is that I do an experiment, I repeat the experiment, I get the same result, and then I say that you do it. You can also repeat the experiment and you get a consistent result. And we assume that anybody doing that experiment at any point of time will get the same results. This is what is called as consistency of research. So Feyerabend refuted consistency. Feyerabend also refuted falsifiability by a very interesting argument called the tower argument. He was saying that if the Earth is rotating, if a ball is dropped from a high tower, the path of fall should be slanting, because by the time at which the ball starts from top, and by the time at which it reaches the bottom, the earth would have moved a bit. So the path should be slanting, but it doesn't. It is not so. It falls really vertical. So he says that the tower argument says that, see, at that point of time, the theory says that the earth is static. It was the theory. The theory was saying that the earth was static, and uh, all the planets are moving around the around earth. That was the dominant paradigm at that point of time of doing the tower experiment. And then you put a ball and see that your results are fine with the existing paradigm, because earth is static, earth is remaining still, so the ball falls vertically. So when your observation is extremely likely extreme, even if your observation was going in tune with the extreme with the existing paradigm, what Galileo did was to refute it. Even though the experimental result was in tune with the existing paradigm, he kept that result away and pushed his theory forward, saying that no, Earth is not static; it is moving around Sun. So Faraman takes up a large number of cases in the history of sciences, including the scientific revolutions, and says that this theory doesn't work. It has not worked in history. Sciences. This is not the way science has progressed. So you cannot put definitive prescriptions on how to do science. Science is basically an anarchist enterprise. So that was the position which was taken by Paul Feyerabend. And he also argued that just like uh, religion was separated from state, religion and state was one single parcel at one point of time. It was severed and it was separated. Religion is different, state is different. Now he also put the argument that science should be separated from state and subject to democratic control. Common people should be able to evaluate what is happening in scientific institutions and laboratories, not the state. So he wanted a severing of science with its relationship with state. Now, I give before closing, I'll take a philosophical problem in biology. There could be philosophical problems identifiable and explainable in physics, chemistry, and different subjects, but I take biology for the example because I am a biologist. Uh, Now, the simple way of describing this particular problem is that you know what a species is. We are a species, Homo sapiens. Uh, we go by the binomial name, the genus name and a species name. Homo is the species name, and sapiens is the uh, species name. You also know that in the genus Homo, there were other species also. The Homo erectus were there. Many other species of Homo genus were present. And this is the view we have about a species. Now, an interesting question is whether this is a natural category. For example, you can see a picture of a picture on the top right corner. It's a picture of a grasshopper, a pygmy grasshopper. What is interesting is that this was discovered very recently, and the paper was published last week. And what makes us very happy is that look at the name of the species. It is Cladonotus paskeri. Paskar is our Paskar. It's our student in the entomology department, Thanesh Paskar. It is based on his name that this species is named as Paskari. It was discovered from the rainforests of Sri Lanka by a group working there. And it was a discovery in that particular group for the after a period of nearly more than a century, exactly 116 years. After that, there's a new species coming up in that particular group. Now, the question is, are these species waiting for discovery that this particular species, when you call it as particular species as Cladonotus paskari, what does it really mean? Are these quite natural entities out there? Now, now we come to a particular process in process in science in which we normally classify as we are Homo sapiens, and we call many other species with the normal name, and we classify them into a hierarchical system. So we are Homo sapiens, and we are in the hominid family, and the order is primate, and we belong to the class Mammalia, uh, and the phylum Chordata, and we belong to the animal kingdom. So this is the way we arrange it, as if this is a very solid category. It's a solid category of one species called Homo sapiens. Now, uh, uh, we also understand how do you define a particular species. We normally define a species saying that this is a uh, group of organisms, similar organisms, which can freely interbreed to produce viable offsprings. So this is a classical definition for a species. Now, this doesn't hold in many of the cases. Like, for example, hybrid zones. There are organisms in the case where hybrids are formed and which are also viable. Once in a while, they become viable also. Not that all are or uh, uh, incapable of producing offsprings. Now, another complexity comes in when we look at the actual species composition. We come to with a very interesting phenomenon called the ring species. What's a ring species? You can see it over here. Now, if you look very closely at this picture on the bottom right corner, there are A, B, C, D, and E are there, and you can see this uh, uh, arrow marks. Double arrow marks can be seen across all these different things. What actually happens is that uh, here A is a particular group of organisms, B is a particular group of organisms, and there is interbreeding possibility between A and B. And there is also interbreeding possibility between C and B and C. But and also interbreeding possibility between D and C, and also between D and E. This interbreeding really happens. But the problem is that there's no interbreeding possible between A and E. So where do we call it as a new species? Which all are can be treated as different species. You you cannot call A and B as distinct species because they interbreed. You can call you cannot call B and C as different species because they also interbreed. You cannot call C and D as different species because it is they can interbreed. It's not possible between D and E also. So now, if all this can interbreed with the immediate neighbor, you cannot call any one of these as a separate species, but you are forced to call A and E as different species. And if you call so, what is going to happen between A and D? Because E can mate with a D. So what do you call between E and C? Are they E and C different species? You cannot call it so because they both can interbreed between D. So and this is the problem with the ring species. So what essentially means is that you cannot classify a particular species as a single definitive group. Darwin, when he was speaking about species, he told that species is a word which he wrote in Origin of Species. What he told was that I cannot call this a different, uh, absolutely different group. I will quote the exact sentences which he wrote. It will be seen that I look at the term species as one arbitrarily given, for the sake of convenience, to a set of individuals closely resembling each other, and that it does not essentially differ from the term variety, which is given to less distinct and more fluctuating forms. So Darwin was not very sure about what a particular species is. There are other words also used, subspecies, differences which you see within populations within a particular species, and varieties. So there are many varieties possible. So where do you draw this particular uh, uh, line? Now this came up with the uh, a new explanation from the part of the German biologist Ernest Mayr. He formed the posited the term as a biological species concept, which rejects the Darwin's argument. What essentially Mayr was uh, trying to say uh, there are varieties, but at the same time there are species also, and varieties can interbreed, but species at the level of uh, 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 non-producing viable offsprings. Uh, but see, this has also got serious uh, objections based on how you draw a specific line with the individual species. So one of the problems the taxonomists face is between the practical necessity and the theoretical impossibility. You cannot theoretically call a particular group of organisms as a species, but at the same time, it is practically needed to call it by a name or to take science forward. So um, now, in 1960s, what happened was that there was a notion that whatever way you classify things, organisms, it should be consistent with evolution. That was the idea which was put forward later. For example, if you classify a set of species as a set of organisms as a single species, all of them should have a common ancestor, not just the species, but any higher taxa. But interestingly, this is called as a phylogenetic approach, where two organisms belong to the same group, either species or higher taxon, because of shared ancestry rather than their intrinsic similarity. So, when you come to the phylogenetic approach, what essentially means that it is not the similarity across different individuals that makes it into a single species, but it is the question whether they have originated from a single ancestor. So, if even if you see a large number of organisms which are quite similar, they are interbreeding. That is not enough. They should have evolved from a single ancestor. Now, that also faced with a problem because here is the evolutionary tree for reptiles and the birds. The if you call the first three, the lizard, crocodile, and the dinosaur as a reptile, the problem is that the birds also come on the same line because the birds also originated from the same ancestor, just like the reptiles had. So the phylogenetic approach doesn't work over here because if uh, you need to call these three as a single uh, uh, group, a higher taxa called as reptiles, what do you do with birds, which also is in the same stem of evolution? So taxonomy says that reptile is not a valid classification in taxonomy. So it is the inconsistency of that. So basically, phylogenetic approach when it says that uh, this should have originated from the same ancestor, there was an interesting theoretical experiment which was done. The case of the Martian housefly. You know the housefly. So think of a situation where we identified a housefly in Mars. We have our Mars expedition. You go to Mars and you find a housefly over there. A housefly which looks exactly like the housefly on Earth, and they interbreed also. But can we call it a single species? As per the phylogenetic approach, we cannot, because we know that they have not originated from the same ancestor. Now, this is the way philosophy engages with the work which we are doing. It questions the primary assumptions which we have taken to take things forward. It looks very closely to how science operates and brings up the chinks in the armor. And that is what philosophy essentially do. The general acceptance of this particular species problem at this point of time is that biological species should not be regarded as a kind or type at all, but rather as a complex individual extended in space and time. It's a complex individual extended in space and time, has a finite lifespan, and then goes extinct. So this is the way we have a look at species now. Now, we need to define species not just for sexually reproducing organisms. There are many plants which vegetatively propagate, uh, asexually reproduce, and there are a large number of microorganisms like virus, bacteria, or fungi, which have got totally different reproductive strategies. And how do you call a bacteria as a single species? There are many different words employed for that. We call it a different strain. And where do you draw the line between two different species of a bacteria or a virus or a or a mammal or a bird? Now, This is the way philosophy intervenes with the sciences. I'm coming to the last part of the lecture. Oh, sorry, it's taken a long time. Uh, is there any critique for science? Yes, feminists say that there's a large. They say that this is basically a male-dominated enterprise. How come? Basically, if you read the textbooks, if you look at the reproductive in the school textbooks, we say that if there are specific statements which says like this: if you have got if a particular egg produced by a female body is not fertilized, it is wasted. So that's a specific word which will be used over there. But the female body produces only one egg per day, per month. But there are millions of sperms produced by men, but nobody calls it that's a waste. So if you look very closely at the text and the practice of science, feminists have identified large number of examples like this. It says that this is basically a male enterprise. And secondly, from peoples with religious views, say that their faith is going to be questioned by science. It just happened. You know the case of classic case of Galileo when he told that the Earth is moving around the sun. Big uproar happened from the Catholic Church, and he had to pull back his statement. The classical statement he told that I can say that the Earth is static and stable, but still, when I am saying this, the Earth goes around the sun. Now, people with the religious views have got problems with science. Anthropologists also have a objection to science, saying that science has become an overpowering entity which ridicules other knowledge systems, especially the knowledge systems of indigenous people. Their beliefs, their worldview is being put down by science. So there are many critics possible. Now, we need to take care of a few things like scientism. The major criticism which is against science. Scientism is a process in which you believe science just like a religion. Whatever science says, you take it and move forward. And that is a process called scientism. Worshipping science is called scientism. Like, for example, when there was a problem with endosulfan in Kasagod, there was a group of scientists who would say that uh, this is not caused by this particular pesticide. And the reason why they told that our experiments have not proved it. So this is one classical case of scientism. You worship science and you doesn't question what it essentially does. And science and religion, there's a major debate happening between science and religion in the sense that in the US it was very popular whether to teach creationism along with Darwinism, and they resolved it by saying that you can teach both and let the people take whatever they feel like. So there's big criticism coming from the part of religion, and in India is also it is getting much more popular in the sense that almost all the advancements of science is now tried to be tied to some of the existing knowledge in poems and stories and all. So there's a critic happening with in that particular dimension. I come to the last part is the question is whether the science is value free. Is practicing science a process in which you go out and do science without any value system, any morals involved? That's a big question which science is facing uh, right now. Is it a value-free, value-neutral enterprise? Philosophers say that no, it is not value-free. When you select your topic of study, when you decide what you study, you have a value system in mind. And when you collect your data, when you try to interpret it, what theory you are going to use is also influenced by the value system. And you cannot completely divorce the science you practice and its possible implications. Like, for example, the best scientists in the world once put together to create an atom bomb. And when they are working on it, they knew that an atom bomb is going to be created and the atom bomb is going to kill millions of people. So the science, it was brilliant science which they were doing, but then they knew that it's going to have a specific uh, uh, consequence in the history of humanity. And many of the scientific interpretations, scientific uh, things are also being debated. For example, genetics. It is known that people have got different behaviors infused by the genetic structure. And evolutionary biology also says that for every being, what every individual does is to try to propagate its genes as best as possible across the uh, population. So that's a drive. That's an evolutionary drive every individual has. Every a crow would like to expand its gene as broad into its population as possible. Now, when you take it into sociology, the problem happens is that uh, think of a person, think of a rapist, a person who rapes women, and you can explain his behavior in the sense that you can say that that man is driven by a evolutionary drive, which makes him spread his genes as wide as possible. Now, this is a problem when you copy paste scientific hypothesis. So, what is essentially needed is to understand that value is different from data. Data is different. Value is something else. Now, um, I stopped here. Uh, what I was trying to do is to tell you what philosophy of science is doing in sciences. So, thank you for patient hearing. I'll be happy to take any questions you might have. Thank you.
Thank you, sir. Thanks a lot for such an informative session. So we have a couple of questions.
Yeah, tell me.
So one question is the distinction between observing and detection is merely one of using our senses to see, touch, hear, etc. on one hand, and use of devices or instruments to detect what is not possible by the former?
Uh, can you repeat the question?
Uh, is it the distinction between observing and detection is merely of using our senses? And for detection, is it with the help of devices or instruments? Is that the way of distinction between observing and detection?
Okay. Okay. See, what we have done in sciences is to expand our senses. Like, for example, the human eye can now see a particular object of a particular size. We have expanded it. You can now see long distances using a telescope or a binocular. You can now see small things using a microscope. But there's still observations happening. But then there are other things which you cannot observe, uh, which is beyond our sensory capabilities. That is what we call as the detection. Like, for example, you say that there's a uh, thing called atom. You are not observing it, but then you are detecting it based on some other indications which is happening. So the distinction is between not just our sensory five senses and the expansion of those senses. Beyond that, there are data which is gathered, which is called as detection.
Okay, sir. Thank you. So next question is, uh, Darwinism is not a testable scientific theory but a metaphysical research program. Just as Freud's explanation of dreams, Darwin's theory tries to explain observations with the assumption that it is true even if it contradicts itself, which is basically what a typical religion does. How would you comment on that?
Yeah. This also falls under the category earlier, where the natural selection is operating over there. So, what is essentially happen is that what distinguishes Darwinism from a religious position is that, as I told you earlier, this is a empirically testable thing. You can verify it. You can observe, you can experiment, and you can collect data and say that this is happening this way, irrespective of the person who is doing it, irrespective of where it is being done. So this is the empirical element is the one which distinguishes Darwinism from religion. Any more questions, Krishna?
So last Last question. Hope this is the last one. Is there any argument at all for retaining any control of state on science and keeping it undemocratic? It should be obviously not be so.
Can you just repeat the question?
Is there any argument at all for retaining any control of state on science and keeping it undemocratic?
Yeah. Basically, science needs freedom, and whenever institutions were started, scientific institutions were started, it had started with a large amount of autonomy. Almost all institutions are started autonomous, so that while the state funds it, it doesn't control it. Like, for example, you have the Massachusetts Institute of Technology, where you have people like Noam Chomsky working, who is a very heavy critic of the state out there, but he is working in a university. And scientists were free to express their views and to conduct experiments at their own discretion, while the involvement of state was limited to the support of the institutions which were conducting research for common good. But more and more control is being exerted. Academics is being heavily controlled by state in the recent years, which is going to be a very bad trend.
Okay, sir. Our questions is over. Anyway, thanks a lot for your great talk. I'm so happy to hear from you every time. It used to be like that. Thanks a lot, sir, on behalf of AKRSA and all participants. Thanks a lot. Thank you.
Thank you. Bye.
Okay.